results that I can tell you about, but it's one where, as I'll hope to try to convey in the middle part of the talk, the interest is more in potential developments in various directions in the future. But it also connects with familiar mathematical things of a classical nature. So let's begin with those. This is this first section. I'll set up what we want to discuss. So if we go back to just one variable complex analysis, then we're familiar that it's useful to consider, at least speaking, multi-valued functions, such as the square root of f of z, which if f is, say, f of 0 is 0, simple 0, this will not, of course, be a well-defined function on the face of it. On the neighborhood of 0, as we go around 0, sort of follow the function around, the branch of the square root will get changed, and so the function will come back with a change of sign. But we're quite familiar with how to make sense of this. We can either we could talk about interpreting this function on a covering space, or another notion would be to talk about a flat bundle over the punctured plane, and this object is a section of that flat bundle, not really a function. So if we have such a thing, then we can take its real part. This locally will be a harmonic function, as well known, and again, with multi-valued. So this is the kind of thing that I mean in this classical context by a multi-valued harmonic function. Now, what we want to do today is to consider generalizations of this classical setup in higher dimensions where we have an n-dimensional manifold and some codimension 2 submanifold, L, and so in this situation, of course, we have a Laplace operator defined by the Riemannian metric. So we want to consider similarly things which are locally away from L, locally composed of harmonic functions, but are multi-valued in the sense that if we go around L, then the function will change sign. Actually, the main case of interest for me is the case when M is 3-dimensional and L is 1-dimensional. So, but L will be a link then in a 3-dimensional manifold. So we're considering the picture that we go, if a function u, as we go around, u sort of changes to minus u. So let's just think initially locally about this. We can introduce local coordinates adapted to this setup. So a coordinate, say z, a complex coordinate transverse to L, and t, a coordinate along L. So local coordinates. So one thing one has to do, which is a sort of prerequisite for what we're talking about, but we won't go into the details, is to have some suitable analytical foundations for handling these things, which amounts to adapting the standard, or a variant of the standard elliptic theory for operators like the Laplace operator to take account of this sort of situation. But such theories are quite well established. One can, so a variant of standard elliptic theory. So the basic point is that functions like root z are things we want to consider. That's the paradigm what we want to consider. And of course, the derivative of root z is not bounded. So whereas in ordinary elliptic theory, if we're studying harmonic functions, then on an interior, all the derivatives are nicely controlled. We have to have something different here. So what one considers is functions where, say, u is in some Holder space, C alpha. The second derivatives in the t direction of u are in C alpha. But we can't control the radial derivative in C alpha, but we can only control, say, r squared times du dr squared, where of course z is r e to the I theta in the usual way. And similarly, we can only control d2 u d theta squared. So all of these are in C alpha. So we consider functions, or particularly these multivariate functions satisfying these conditions, and then the Laplace operator, as we've literally defined it, that maps into the Holder space C alpha. So the crucial thing is to construct a parametrics for the Laplacian. So essentially, speaking, an inverse or inverse modulo lower order terms for the Laplacian. That's to say, if we have a function where the Laplacian of u is in C alpha, we can control all of these other derivatives. Anyway, such theories exist. For example, as developed by Matsuo. These are what Matsuo would call wedge spaces. And we won't say any more about that aspect here. But the crucial thing that one gets from the theory is that if we have one of these multivariate harmonic functions we're talking about, we make some mild assumption to control the behavior, say bounded, for example, then it has an asymptotic description. But u is given by, say, the real part of some a, what's my notation? Al, function t, times z to the 1/2 plus v sub l of t times z to the 3/2 plus higher order terms. So the basic question we want to discuss is if we have some suitable global problem, one example of which I'll explain in detail in a few moments. So far we've had L is fixed. Supposing we can solve our problem, and then we will get this object A, this leading term. Can we, on the hand, if we vary L, can we arrange that this leading term is 0? So given a suitable global problem, can we choose vary L to make AL equal to 0? This is the basic kind of question we want to discuss. In a few moments we'll describe a precise problem of that kind. Now this question has a somewhat similar nature to a free boundary value problem. If we were studying, let's say, the Laplace equation on some domain in Rn, then you could impose Dirichlet boundary conditions where you fix the function on the boundary, or Neumann boundary conditions where you fix the normal derivative. But you could ask, can I fix both things, impose both boundary conditions at the cost of allowing the domain to vary? That would be a typical free boundary value problem. So this is analogous, except instead of the codimension 1 boundary, we have this codimension 2 set that we're considering. But let's now be a bit more precise and spell out precisely one global problem in which we're going to study this question. So I'm going to put a model. So this will take a little while to set up. Let G be the isometry group of R. So this is generated by translations and reflections. So G is a group. It contains the translations of the R, the group under addition. On the other hand, it has a map to the group of order 2, depending upon whether you change the direction in R or not. So let's suppose we're given a homomorphism rho from the fundamental group of the complement M minus L to this group G. Then using that, we can construct a flat bundle with fiber R over the complement of L. This gives a flat. So that's just to say, as we start at a base point and we wander around in M, avoiding L along some path, then as we parallel transport in this flat bundle, we come back with something different given by the action of this thing R. So we're allowing ourselves to change sign, but also to shift by translations. So anyway, the objects we're going to consider now are sections of this flat bundle. But if you're not so familiar with bundles and things, you could just think of their functions, and this is a convenient way of talking about things globally. No, it'll have just the fiber will be the real numbers.
Oh, real numbers.
It won't be a vector bundle because we have these translations. Yeah. So a section is just a real value function locally. From another point of view, we can form what's called the double-branched cover. Of M branched over L, just as is familiar in the Riemann surface situation. And so, well, U, because these translations, U will not itself necessarily be well defined as a function on the double cover, but its derivative du is a closed one form on M tilde, and so has some cohomology class du in H1 of M tilde. And in fact, this will be anti-invariant under the involution of M tilde. So M tilde comes with a map from itself to order 2, which interchanges the sheets. And by construction, this thing will be anti-invariant under the -1 eigenspace of the action of sigma. So let's write minus here. And in fact, this data of getting this representation or this flat bundle, another way of expressing it is that we have this double branch cover and this cohomology class in the anti-invariant space of the cohomology. So rho is equivalent to giving M tilde and this class of du. So that's, now we know precisely what we're talking about in the sense of they're not really functions, but sections of this bundle. We want to consider harmonic sections, so solutions locally of the Laplace equation, which can equivalently be thought, for thinking in terms of the derivative, is essentially equivalent to talking about harmonic one forms on the M tilde, but with respect to a singular metric, with respect to the metric you get by lifting up G to M tilde. So either way, it's a standard fact that there is, in this situation, a unique harmonic section. It's a version of the Hodge theorem for this singular metric, or you can think of it as arising by minimizing over all sections U the Dirichlet integral, the L2 norm of the derivative. So basic fact. This is a unique harmonic section U. I mean, if we impose some, let's say it's bounded, or any kind of mild regularity condition to rule out some bad singularities. So this section has an asymptotic description of the kind we were saying, and so it has in particular a leading term, A. So this A is it depends upon what our data, this rho, the Riemannian metric G, and L, and what is globally, here we were sort of thinking somewhere in a local description where we could just think of A as being a complex valued function on a function of the variable t along L. Globally, this turns out to be a section of a bundle over L. In fact, you can think of this bundle as the square root of the normal bundle. So n is the normal bundle. But let's not worry too much about that. Exactly. But this object A is a section of a certain natural bundle that we have over L. Because it's a complex line bundle, right? A rank 2 real vector bundle. So our model problem, then, in this situation is to say, well, the general problem we'd like to understand would be if we're given a rho and a g, can we choose L to make A equal to 0? That's the general problem, but we're not being so ambitious. We're just wanting to discuss a deformation version of that. So suppose there's the model problem. Suppose we happen to have a collection of data L0, G0, and ρ0 equal to 0 for ρ and G close to ρ0 and G0 in some suitable sense. Can we find L close to L0 such that A of rho G L equals 0? So we're just discussing a local perturbation version of our more general question. And I say, well, it's a model problem because there are many similar questions we can just stay within the world of linear equations. For example, we could solve not delta U equals 0, but delta U is some given source term or something like that. Or lots of other, we could have a manifold with boundary and vary the boundary data. Or many other things we could do, but essentially they would all, the essence of the problem would always be the same as regards to the fundamental question we're looking at. So the answer is, the answer is yes, provided the next term, B of ρ0, G0, L0, is nowhere vanishing. So if we're supposing we have original data with the naught, so that this term is 0, and the next term comes into focus. If this doesn't vanish anywhere on L, then under that condition, we can solve this perturbation problem.
Does this have any hypothesis like compactness of M?
Oh, right. Yes, sorry, I should have said. M and M is compact.
So is P out the same the same line bundle as A out?
No, BL will be a section of the minus 3/2 power. That's what, globally, for this to make sense. Okay, so that finishes roughly on time. The first section, this is the problem and the result, is it, that we want to talk about today.
If B vanishes somewhere, there's some more refined condition where
it could be, but I don't know that I don't. That would, yeah, I don't know. So I should say that yes. So it is relevant. Maybe say that if the main case of interest, I say, is when L is one-dimensional. So since B is a section of a bundle of real rank 2, you expect that generically it shouldn't vanish in that case. In higher dimensions, that will become more restrictive. Well, that's the whole point of the talk. How you prove that. But I'm not going to. The last section is to talk about the proof a little bit. The next section is to talk about motivation. Why should we be interested in? I mean, it seems perhaps a bizarre thing to be interested in. So maybe I'll four parts of motivation. One is this if we go to the classical case of n equals 2, then this fits in with some sort of well-known, interesting theory. So we're discussing Riemann surfaces. Because the harmonic condition only depends upon the conformal class of the metrics of the Riemann surface. So we're considering familiar double-branched cover, and L is just a finite set, this branching set. So as I said, if we have one of these harmonic gadgets, then the derivative du is a well-defined one form on M tilde. And in fact, it can be viewed as a holomorphic one form. On M tilde. But if we take du squared, then that's well-defined on M and gives a well-defined quadratic differential on M. That means a section of the square of the cotangent bundle in the usual way. So the condition that U is, in terms of a local coordinate on M, U is like behaves like z to the 3 over 2, the condition that the leading term is 0 means that du is like z to the half, dz. So du squared will be like z dz squared. So this quadratic differential will have a 0 at this point of L. If we didn't impose this, if we allowed u to be like z to the 1/2, then this quadratic differential would have a pole. So the condition we're looking at is very natural because it's just demanding this quadratic differential be holomorphic. But taking another point of view, start with a generic holomorphic quadratic differential with simple zeros. The number of zeros will be given by twice the Euler characteristic. So minus the Euler characteristic, and form the double-branched cover. And then we have these periods. So the genus of M tilde, if we use the Hurwitz formula, we can work that out. That is equal to 4g minus 3, which means that the dimension of H1 of M tilde is twice that, 8g minus 6, whereas the dimension of H1 of M is 2g. So when we look at we can decompose this cohomology upstairs under the action of the involution. The invariant part just corresponds to the cohomology downstairs. So the dimension of the negative subspace is just the difference of these two. So dim H1 of M tilde minus equals 6g minus 6, which is the dimension of the quadratic differentials, the holomorphic M. So this sort of simple dimension count fits in with our statement in that case that on an open set, let's say H, contained in the quadratic differentials, on some open set where we have simple zeros, and we have at least a locally defined map to this R 6g minus 6, given by taking the cohomology class of its square root on the double cover, and this is a local isomorphism. Given by these so were the periods of the quadratic differentials, but you take them upstairs so that you can take the square root. Another motivation is the potential application to special Lagrangian geometry. So I should emphasize what I'm talking about here is that something one might hope to be able to do. It's not something which I have done. But as I said at the beginning of the talk, the main interest is on directions for the future rather than what's already been done. So let's just think generally, supposing we have some manifold X and a minimal submanifold M, then an interesting phenomena to consider is a sequence of minimal submanifolds which converges to, as it were, twice M, in the sense that, in a natural sense, that two sheets of things come to collapse onto M. So we can have Mi converging to, of course, any multiple of M, but twice in our discussion. So one would like to study how that can happen. We'll be talking in the particular context of the minimal submanifolds, which are what are called special Lagrangian submanifolds in Colloquium manifolds. But I won't take the time to define what those things are, but I give the general idea. So these special Lagrangian submanifolds, this is a notion developed by Harvey and Lawson in their famous paper on calibrated geometry from about 1980. So special Lagrangian. Well, let's just first consider the Lagrangian condition. I won't define it, but just to say if we take a local model, Rn times Rn, with coordinates xi here and yi here, then essentially the general Lagrangian submanifold will be constructed out of a generating function, f of x, by taking the graph of the derivative. So we take the graph yi is df dxi. So this will, we have x and y, this will define some submanifold like that, and more or less, speaking, this is a general way of constructing the general Lagrangian submanifold. The special condition is a further condition which then becomes a differential equation for this generating function f. Let's just take the case, it's not the same n as we had before, m equals 3. Then the special equation in the simplest setup will become the equation of the Laplacian of f. Well, it's not quite the Laplace equation, but then we take a very nonlinear term. We take the Monge-Ampere term, the determinant of the Hessian, is equal to 0. So that's a complicated nonlinear equation, but if we're thinking about small variations about the case f equals 0, then the linearization is given by the Laplace equation, because this is a cubic term, the linearization. So what that means is if we're studying small deformations, what these special Lagrangian submanifolds are essentially given by harmonic functions of the manifold. If for one of these multi-valued harmonic functions, one could imagine that if we take the graph of the derivative of complex notation. If I take the derivative of z to the 3 over 2, it's 3 over 2 times z to the 1/2. So being a bit vague about real and complex, if I take the graph of the derivative of a function like that, I will get something like that. And if I multiply the function by a scalar, I will get, roughly speaking, a sequence of solutions of the linearized equation which collapse down to a multiple cover if you're given special Lagrangian. So I think in order to have time for the last section, I'll just condense. I had 4 motivations, but I'll just condense the last 2 into a few words. But just slogans. Three. So collapsing of Einstein manifolds. So here we have the pictures. We're studying, say, the Einstein equations or some variant of that, some special solutions to the Einstein equations on some manifold Z. And we're looking at solutions which are, roughly speaking, fiber bundles over some manifold M, but with some singular fibers over a discriminant set L. Then one can hope to model the adiabatic limit of the Einstein equations, and the limit as the size of the fiber shrinks down to 0 by objects like the sections U that we were considering. As we would get flat bundles coming from the cohomology along the fibers would define a flat bundle over the manifold minus the discriminant set. And we would get nonlinear equations for sections of these flat bundles. Well, I think I won't try to say any more about that. Another one is singularities in gauge fields of various kinds, or various versions of the Yang-Mills equation or related equations, which have been studied a lot recently by Taub, arose in work of Taub's and Takahashi. Also related to work of our own Alexander Doan with Valpusky and Hadis. And in fact, also related to the work of Yankee Wang, who was a postdoc here until recently. So I don't think I like time to try to talk about this, but there are various contexts in which singularities are appearing in new ways, in which understanding this, the analogues for perhaps more complicated equations about this question about deforming the singular set is an important issue. Okay, so let's get on to have some amount of time for the last section, in which we want to talk about something about the proof, or the solution of this model problem. So, as Draw pointed out, this looks like a question which could be perhaps solved by rather standard routine methods. So let's ignore that. Let's just take the is considered the part of the data given by the metric for simplicity, just to save notation. So we have a section 3 solution of the problem. So let's just ignore this row and just think of A of G and L. So this is a section of a bundle which depends upon L. So we don't precisely have a map from the space of G's and the space of L's into some fixed space. But if we're just considering small deformations, we can identify all the L's near to a given one in some standard way. And so we can think of the space of sections as being a fixed object. So a standard technique is the implicit function theorem applied in Banach spaces, in function spaces like the Hölder spaces and things that we've mentioned briefly. So let's just recall in outline what this is. If we have three Banach spaces, U, V, and W, and we have some smooth map from U times V to W, F, then this has partial derivatives that are right as df du, df dv, partial derivatives. So df dv, for example, is a linear. It depends upon a point. At a given point, it's a linear map from V to W. So the implicit function theorem says that if we're at a point where this is an isomorphism, this partial is an isomorphism, then locally near that point, the equation f of u v equals 0 defines v implicitly as a function of u. So that's just what we would like to do, because we would like to say that the equation a of g L equals 0 defines L as a function of g. For each nearby g, we can move L in a unique way to satisfy that equation. So it looks as though we're all set up to apply this standard technique, provided we can fit things up with some function spaces and so on. So this gadget is a smooth map with and the partial derivative is an isomorphism. If we had all that, then everything would be completely routine. So the question is, what is the derivative of this? What is the derivative of this A with respect to L? That's the crucial thing we want to know about. So what is this going to be? This is going to be a map from, so the derivative of L, how you're deforming L by a vector field, a section of its normal bundle. So this derivative has got to be a map from sections of the normal bundle to the place where A of GL lives, which is the sections of the normal bundle to the power minus 1/2. So what is... So just as a map, it's a map from sections of n to sections of n to the minus 1/2. So that's the thing we have to understand. So I'll tell you the answer. So it acts on a normal vector field V. So it's got two terms. There are two terms in the formula. One is that's an obvious term, in a sense. So this is minus 3 over 2 b times v. So here, b is a section of the so it turns out to be the minus 3 over 2 power of the normal bundle. So this is just the algebraic contraction from the minus 3 over 2 power times n to the minus 1/2 power. This is locally, this is just multiplication of a function b by a function v, complex value functions. So that's, so I say, the obvious term. In a sense, this just comes from the fact that if I take d by dz of z to the 3 over 2, this is 3 over 2 z to the 1/2. So if I just translate my given solution a little bit, that's the translation will bring in this apparent z to the 1/2 term. I'll try to say more about that. And of course, this, yeah, so if you want to, in the Riemann surface case, this would all be the only thing you'd have. The complication comes from the next term, which is given by applying a certain operator defined over L to the other contraction we can do. We take A times V. So where P is a pseudo-differential operator of order +1 on L. To define. So I'm not going to try to say anything about deriving this formula. I'll just say more what P is. I think that'll. Well, in fact, let's not say what. I'll come back to saying what P is, but just this statement tells you why we can't solve the problem using this implicit function theorem thing. Because, so as soon as we've gone away from us, as soon as we have any A, this derivative has got this order 1 term. So it contains derivative. This is something like a differentiating of order 1. So if I have my setup, these are supposed to be well-defined maps, so V must contain more derivatives than W. W could be, say, C alpha functions or something, but then V should be C1 alpha functions in order for this expression to make sense. Or it could be L2 and L21. But you have to have more derivatives on that side. But then when you're at the point, as you are when A equals 0, this is just essentially the identity. This is just multiplication by a function. So that's not the inclusion of L2 in L21 is not an isomorphism. So in other words, although we're considering if we're near the point where A equals 0, this term is very small in that sense. It's large in the sense that it contains more derivatives than this term. Does that make? This is the crucial point. So, sort of see the point. Okay, so we've got 8 more minutes. So I'm going to tell you what P is, and then I'm going to tell you what. Well, but let's do it all the way around. Let me tell you the end first, in case I'm out of time. So the point is that the ordinary implicit function theorem in Banach spaces does not suffice. But there is a more sophisticated theory, going back to work of Nash, then developed by many other people. So it's often called the Nash-Moser theory. The particular variant that we need is, I find it in the paper of Hamilton, a long survey paper in the AMS Bulletin from about 30 years ago. He calls it an idea that originated with Zender. Anyway, by a combination of some more sophisticated theory of Nash-Moser, Zender, Hamilton, there are extensions of the ordinary implicit function theorem which do work in this context. Essentially, although you lose derivatives, if you just do the naive sort of inversion, you lose derivatives, then the theory introduces smoothing operators to put the derivatives back and do it in a careful way so the smoothing doesn't, you can still develop an iterative scheme to converge to a solution. So that's the punchline, is that we can't solve this problem using the most standard techniques, but there are more sophisticated techniques available which do the job. So one could imagine that in these other problems that I really ran out of time to try to mention, the same kind of Nash-Moser theory would maybe have to enter. So the conclusion is that more sophisticated Nash-Moser, Zender, Hamilton theory does what we need, covers this problem. Okay, so I've got 5 more minutes. Let's just go back to saying what this operator P that appeared out of nowhere is. To say the proof of this formula is not, it's sort of basically a standard kind of calculus formula when you do it all. It's not a. So what is P? So P comes from the Green's function of our problem. So remember, the Green's function is a function on M. Well, on n times m, which are 2 variables, but in each argument, away from the diagonal, is a harmonic function. So our discussion of the asymptotics applies. So let's just talk locally in our local coordinates, say z1, t1, and z2, t2, which is the Green's function g of this. We're looking at the behavior for small z1 and z2. So that's going to be given by the real part of something times z1 to the half, z2 to the half, times something depending upon t1 and t2. So plus higher order.
Green's function is for
no, the Green's function for our plus operator on M.
no.
So this is the Green's function for the plus operator on M. So it's a function. These are local coordinates describing points in M, but we're just working near to L as notation. The point is we get this gadget gamma, which is a function of 2 points on L, and P is, well, roughly speaking, P is the integral operator defined by gamma. So P of f at a t1 is equal to the integral of gamma of t1, t2, f of t2 with respect to t2 over L. But that's only roughly speaking. Let's put it in inverted commas, because the singularities of this gamma means that this integral will not be close to being convergent as it stands. For example, on, e.g. on R, if we take the model case of R3, and the standard R in R3, then this, just by the grounds of homogeneity, you find that gamma of T1, T2 is 1 over T1 minus T2 squared. So this is just, so L is just R here, so we're trying to integrate 1 over T1 minus T2 squared f of T2, and of course that's pretty divergent in general. But that's quite familiar and standard, and there is a pseudo-differential operator associated to a singular kernel like this, given by regularizing the integral, subtracting off a counter term in the integral. So the true formula in this, going to this R3 situation, so in fact P of f of T1 will be the limit as delta tends to 0 of the integral over, you take the distance, cut off at the distance delta, so then we take the same thing, f of T2 over T1 minus T2 squared. Then we subtract off, because we know exactly how this is growing, well, with respect to delta. So we subtract off delta to the minus 1 times 2 delta to the minus 1 times f of T1. So if you think for a bit, you'll see that for any smooth function f, this thing will make sense. So this is a standard way of interpreting this kind of singular integral. So in fact, P is on R, in this model case, P is just the square root of the Laplacian. So it's always, on a general L, it will be some pseudo-differential operator with the same symbol as the square root of the Laplacian. So a first order operator. Right, so that's all that I have to say. So I say, yeah, thank you.
So like in this, if you have in the three manifolds, suppose L is 1, then this abstraction term basically is like a section of circle bound over the circle, right? So does it mean like the moduli space, the smooth part moduli space has different components classified by this homotopy types of abstraction?
Yes, I think I couldn't quite follow the.
Like B is a section of one bundle over one manifold.
Right.
Well, if it's nowhere 0, then
I see what you mean. Right. Well, that would be true in a one-parameter family. Yeah, you would expect to encounter zeros, and there would be this. That's a good point. Yeah, but I hadn't. Yes, I hadn't got as far as thinking about that. Yeah, no, that's definitely interesting to understand what happened.
You replace this real curve by a complex curve, complex. Is there any possible interest? Do you gain anything by having a holomorphic curve?
Well, you would.
Trying to imitate the Riemann surface case by complex codimension moduli.
Right. Well, that would be much easier because they would be, but no, I think For these kinds of questions, I think you really that would be too restrictive. You would probably get typically no. No, you couldn't impose any other conditions on L, and really because.
In the three-dimensional case, the normal bundle is actually trivial because it's over a one-dimensional base. In higher dimensions, the normal bundle might not be trivial, right? It's just like W2.
That's true. Then you couldn't, yeah.
Difference if the bundle is not actually trivial. It doesn't make
Well, if it's not trivial, then you wouldn't have this hypothesis would not be satisfied. Yeah. So I don't. I just don't know what the theorem would. Maybe there's a way to extend this to. I mean, you're trying to invert multiplication by something with a zero, so no, it's just not. It's definitely an interesting thing to look at next in the future.
Usually, when you think of L as a link, like what sort of linking variance do you get?
Well, definitely that's the interesting case when that L is a link in the three sphere. I don't know what. I don't really know of a good answer to your question. This sort of small deformation result is the only kind of result. Trying to prove that if you made some big deformation, that L behaved in a good way, that would be beyond what we know about at the moment. So I don't know how one could get anything like a link invariant at the present state of knowledge. But there are certainly there may be some vague connections with things that are not link invariants.
Further question or comment? Well, no, let's thank the time again.